Okay, so we need a way to represent the structure and interrelationships in neural networks. And here's where notation comes in. A good notation can really simplify the understanding because it follows the concept and brings out the inner structure. So we will be developing a notation, and the notation should remind you of matrix notation. And in fact, matrix mathematics underlies neural networks. All right, so here's our neural network with layers that we showed before. We have initial inputs by X. So these are the features that are put into the neural network. The neural network has several layers, and the total number of layers is represented by the variable L. In this case, L equals 4, and notice that the number of layers includes the input feature and also includes the output node or nodes. In this case, there's only a single node. All right, the features x0 on any layer may simply be represented as 1. As I said, this feature corresponds to a bias. Different layers can have different number of nodes. So the number of nodes in layer small l is NL. So in this case, we have 2 nodes, not including the bias, 2 nodes, and 1 node in the output layer. Okay, now we saw the connections at each level, and these are represented by the variable theta, but we're going to need subscripts to indicate all of these connections. Right. So if we have a layer L and L plus 1, the number of connections is going to be 1 plus NL times NL plus 1. So why is that? Well, look at this pair of layers here, for instance. Every node here, let's leave off the 1 for a moment. Every node here is connected to every node here. So the total number of connections is the number of nodes here times the number of nodes here. But we additionally connect 1 to all the nodes in the second layer. So that's where this 1 comes from. So 1 plus NL times NL plus 1. Okay, so you can see these particular examples. So superscripts are used to represent the layer number. Right? So theta represents the connections. So if we want the connection between node P in layer L and node Q in layer L plus 1, we represent it this way. Theta L PQ. L is the first layer of the 2 layers we're considering. P is the node in the first layer, and Q is the node in the second layer. Now we indicate the 1 node by the index 0. So for instance, theta 1, 1, 2, connects the node 1 in layer 1 to node 2 in layer 2. That's this one here. Theta 3, 0, 1 connects node 0 in layer 3, this should be layer 3, to node 1 in layer 4. So here you have the labels here. Okay, so you can see that theta 1, 1, 2 is here. Theta 3, 0, 1 is here. Now you can try your knowledge and understanding. The parameter that connects node 2 in layer 1 to node 1 in layer 2 is, what do you think? And try this one. The parameter that connects node 0 to layer 3 to node 1 in layer 4 is what? Right. So the answers, right? The layer is the superscript. 2 connects to 1 here. Layer 3 is superscript. 0 connects to 1. Now you remember we were representing the nodes with the letter A. Again, the superscript is the layer, and the subscript will be the node. Now here we don't need 2 indices for each node. There's just 1 index. Okay, so this would be, well, let's look at these examples. So that's A2, A3, A4, right? So this would be A20, A21, A22. And so on. So the A is used to denote activation. So we don't use A's for the input layer because we use X for our features. Now let's move on to forward propagation. You can see in the structure of neural networks that information is passed forward from layer to layer. Now let's see how to mathematically represent that passing of information. And just to clue you in, the key is going to be matrix notation. All right, so here is a summary of the notation we've defined so far. The layers, the activation nodes, and the connections. In fact, this theta 1 you can think of as a matrix. Matrix here, matrix here, matrix here. These A's you can think of as vectors. So this is very suggestive that we're going to have matrix vector multiplication. Right? So, for example, you remember where this comes from. First you take a linear combination that we denoted by Z. So Z1, 2 is the linear combination, and then you apply a nonlinear function to it. So similarly in all of these cases. Linear combination, apply the function. All right. And you can see it's very consistent. I think you can, hopefully you can see the pattern here. All right. So every one of these nodes can be represented mathematically in this way. Okay. So we have all of our layers, and each layer has its own set of equations. Now this should be very suggestive of linear algebra equation. The first 2 equations here, you can see, take these thetas and multiply by the x's. Same x's, different thetas. In fact, what's going to happen is this x is going to become a vector, and the thetas are going to be represented as a matrix. Similar thing here. The a's are the same in both equations. The thetas are different. They differ in the second subscript. So that's reminiscent of the second row. This first set of thetas is the first row. Second set of thetas is the second row. So the matrix indices are the subscripts. And the superscript tells you which matrix. As I said before, this really represents 1, 2, 3 matrices. And we're going to see that explicitly in a moment. Okay, so here's the slide where we rearrange intermatrix notation. These are a repeat of the equations we had on the previous slide. And you can group these operations as matrix times vector. Same for the second one. All right, so the output of matrix times vector is going to be a vector, and then you apply the nonlinear function to the vector. And you get another vector. Right. Notice the dimensions here. If we're looking between layer 1 and layer 2, as we are here, the number of columns is the number of features plus 1. The plus 1 comes from the 1 feature, right? And then the number of rows is equal to the number of nodes in the second layer. And that's going to be the number of outputs. 2 output vector, and we apply the nonlinear function to that vector. Same thing here. We're looking between layer 2 and layer 3. The number of rows is equal to the number of nodes plus 1 to include the bias. And the number of columns is equal to the number of nodes in the subsequent layer, which is 2. So this gives me a 2-component vector, which is the 2 linear combinations that go into these nodes. And then I apply G to each component and get a 2-component output. Okay. Now we can simply represent the matrix that was here by the symbol that represents the entire matrix. Here X is the vector of input features, and then the output A2 is just G applied to this linear combination. Right? Similarly, Z3, the linear combination into layer 3, is the matrix theta 2. Now that's not theta squared, it's theta 2. So you need to understand from the context whether the superscript is an exponent or whether it's indicating the layer. In this case, it's indicating the layer. And A2 also. This is the values at the nodes for layer 2. And then we continue this way. Now, the reason for the hat here is that this A2 is this A2 hat with the A2 0 added. What is A2 0? Well, A2 0 is always 1. Okay? It's because you always add a 1 to the other nodes as a separate node. So that's the distinction between A2 hat, which gives the nodes, and the A2, which also includes the bias. So that's always going to be a 1. So we can just follow that here. Now we can simply generalize this to any number of layers and any number of nodes in each layer. And the nice thing is that the nodes themselves do not even appear in the equations explicitly. It's all contained in the matrix and the vector. All right, this is the same equation we had before. Z2 is the linear combination. A2 hat is the nonlinear function applied. Then, if you're looking at layer L minus 1, layer L minus 1 comes from layer L minus 2. You get the A hat when you apply the nonlinear function to the linear combination, and you just continue in the same way. And for the last layer, you simply take the outputs from the previous layer linear combination and then form the nonlinear function applied to that. Now here's an explicit example with actual numbers that you can work out in detail. So I'm not going to comment on this in detail. You can look at the slides and see how this works. So if you start with two features x1 and x2 and you give them these values, you can see how the information propagates through this network. So Z2 will be the linear combination at the second level. So we're going to have a matrix times a vector. Remember, you add the 1 to the two features here and you get the result. Then A2 is the nonlinear function applied to Z2. And I think he's using the logistic function. Then you form from that you'll form the A2, which is the 1 added to this. And you multiply that by the vector representing the weights. In this case, it's a vector because there's only one node here. Then you get A3, then you add a 1 to that, and you get the final output. Right. Then A4, I'm sorry, that's not the final output, that's the final linear combination. The final output is going to be the nonlinear function applied to that. Okay. So in this case, if we were doing a two-class classification, the 0.69 is over the 0.5 threshold. So you would predict 1 and not a 0. Now, in the previous example, we showed how the neural network processes one data item. Now, the very nice thing is that we don't need to process the data items one at a time. Using our vectorized notation, we can do all the vector items at once using matrix notation. Okay? So instead of just having a single column that represents the first row, we can represent both rows of data as a matrix, where the rows of data become columns in the matrix. And the matrix here applies to these two columns separately. So everywhere we're going to carry through two columns, and the two different columns are going to give us the results for the two different data items. Here, instead of getting a single vector output, I have two columns, and then I apply the nonlinear function to the two columns independently. And you can see that all these operations do not mix the two columns, they apply to the two columns separately. So all the information from this data item does not mix with this data item. And you get the final result for both data items all at once. This greatly speeds up the computation. Okay, so we got two different predictions for the two different data items, and we're good. All right, we'll stop there and talk about deciphering neural networks in the next video.